Welcome back to Mr. Brown's basement. The Sylvania Halolight 21C509 chassis has landed on my workbench where the magic is going to happen. At this stage, there's not a lot of video, but there's a lot of work. Everyone has their way of doing repair, and I'm going to show you mine. What we're looking at here is replacing the electrolytic and paper capacitors and testing the resistors, but only replacing those resistors that are out of tolerance. I do the resistors and capacitors at the same time. To help keep track where I am, I use a printed list of all the resistors I expect to find. With each resistor, I record the value I measured and whether I replaced it. As I work through testing and replacing resistors and capacitors, I strike them off the schematic. If there are components that aren't on the diagram at all, this is how I discover them. In this process, I'm never far from the circuit guide or schematic as I work through the set. With this particular TV, I have the choice of two schematics, one from Beitman's most often needed servicing information and Sam's PhotoFACTS. Both show all of the TV except for the VHF tuner that's in my set, and both have insets of waveforms in various stages of the circuit. But in this case, I'm going to depend on Sam's because the circuit is laid out so it's easier to follow the signal path. I also prefer it when the tubes are depicted with their standard symbols. To make it clear and obvious to me where I've been, and to a future repair person where someone's been before, I use brightly colored lead insulation or spaghetti on components that have been replaced. In this set, I'm using purple spaghetti. At this point, I am going to start rebuilding the power supply. M1, M2, the two selenium rectifiers, C1, C2A, and C3. My original plan was to keep these selenium rectifiers in place just because I like the look of them. But space is at a premium, so I think those selenium rectifiers are going to fall off. There are some aluminum can electrolytics. I normally like to keep them in place. I sometimes rebuild them. This one I'll keep in place. I'll just disconnect it from the underside so it's there for appearance only. This one over here, I don't know whether this is original equipment. I have a funny feeling that it is, but it's just sloppy and horrible. So I'll either put another electrolytic in just as a dummy in its place, or I'll just take this out. There's another tubular electrolytic right there. It's on the underside where nobody can see unless they look. I don't see any reason to maintain that. That's going to go. Once I take out the bolts that hold in the selenium rectifiers, I'm going to put in a terminal strip to rebuild the new power supply right over here. And I've been able to identify many of the components in the power supply, label them, and figure out exactly how they're hooked up. This capacitor here, that was that can that was hanging on for dear life, that looks like it was original equipment, and I would call it poor workmanship. Reason why it was mounted in that strange way was because the negative terminal is not at chassis potential or ground. But there are better ways to mount capacitors in that case, usually neatly with a washer, not just haphazardly with a washer. The way I determine how to rebuild a particular power supply depends on the space I have available and the components I have on hand at the time. In this case, I have some very long, that is 8-lug terminal strips with 2 grounds, and a mixture of axial and radial mount capacitors. Here's what I came up with. Here's the schematic of the power supply, and here's the terminal strip I'll be using. This is the way I laid it out. And this is how it looks. That was easy. Now comes the hard part. The next task, replacing all the old electrolytic capacitors with new ones, and replacing the paper dielectric capacitors, that is, waxed paper, Black Beauty, Bumblebee, mica mold, and others, with plastic film capacitors. And checking that all the carbon composition resistors are within tolerance, and replacing the ones that are not. Okay, but where to start?
How about you decide this with rock, paper, scissors, lizard, Spock?
Okay, I can do that. I always start at a tube socket. Let's start at this tube socket, which happens to be a 6SN7 tube being used as the vertical multivibrator. Most octal sockets like this one have pin numbers stamped on the bottom of the socket, but if not, or with miniature heptal or novel tubes, you can always determine the pin numbers using the socket's indexing notch or gap. I make a drawing showing how each nearby component connects to the socket. Then, comparing the socket to the schematic, I identify which component is which. It's only then that I can start testing and replacing components. Understanding one part of the puzzle helps with the next part, and so on. Often, the terminal strips are the most confusing to decode because they aren't necessarily associated with a single nearby tube socket. I've begun testing the resistors under the high voltage cage. This one, this one, this one, this one. They're all out of tolerance. The resistors in this section get baked because the horizontal output and damper tubes are immediately above and tend to run very hot. This capacitor here, it doesn't exist on the SAM's placement diagram or on either schematic. It was probably added later on in the manufacturing run to improve the TV's performance. It's not the only change I've seen so far. I know someone in the comments will say, "Mr. Brown, why don't you depend on the component placement diagrams?" I don't, because they're generally hard to read and because they often contain errors and omissions. I do use them as a backup to confirm what I've already traced out. I've been saving the sync separator circuit for last. It's an analog filter whose purpose is to extract the sync pulses from the composite video signal. It outputs horizontal sync pulses and vertical sync pulses to their respective multivibrators. If this section is not operating properly, it will be impossible to get a stable picture. Let's take a look at the circuit. What makes this circuit non-trivial to measure is that you have groups of resistors that are in series parallel. For example, the measurement of R26 will be affected by R27 and R28, but the measurement of R28 is affected by R66 and R67. To properly measure this, a bunch of resistors will need to be disconnected at one point. Since this filter is populated by mostly 5% resistors, I'm expecting to find many of them out of tolerance. In part 2, I noticed there was missing veneer in a couple of places on the cabinet. I've obtained some mahogany stain and some edge banding. I want to find the right combination for a close color match. Here is mahogany stain on walnut. It's too yellow, I think. Here is mahogany stain on cherry. I don't think so. Here's mahogany stain on mahogany. The lower one is close. I'm going to get some oak and see if I can do better with the oak. In the first part of this video, I removed the Halolight transformer and tested it. Unfortunately, I determined that the 860 volt transformer had an open primary winding, but I decided the assembly housing the switch could be salvaged. I hadn't made up my mind how I would fix the Halolight, though I was considering 4 options, 3 of which include using the original Halolight tube if it's any good. What I'm going to do to figure out if the tube is working is connect it up to a 350 volt power supply, one of these boost converters. I've got it set to 350 volts and I've got a series resistor which should drop the current to about 7.5 milliamps worst case. 2 things I want to find out. First of all, does the Halolight bulb actually work? And second, what color is it? If I decide to match it with LEDs, I want to know roughly what color it is. Now, whether it works or not may or may not change the arc of the repair, but I'm still curious. And the answer is conclusive. The Halolight tube does not seem to be working. There's no light coming from it at all with 350 volts through 50 kilo ohms. Not even a flicker. I'm going to see if I can crank up the voltage. I've got the boost converter at maximum, or at least the maximum it's doing with this input voltage, 650 volts. And it still looks like I got nothing, though I'm going to turn off the light to verify. Yeah, nothing. I think it's fair to conclude then that the Halolight tube is faulty, which means a number of my options have now been ruled out. I'm going to have to go with a solution that uses LEDs. I'm officially waist deep into this TV restoration, but there's still a day or two of work to do before I can attempt to power it up for the first time. Once that happens, hopefully without a hitch, I can start focusing on the smaller details like the picture and sound adjustments, the cabinet, and of course the Halolight itself. I hope you will join me for part 4 when it comes out. Depending on the severity of this Canadian winter, it will determine when I can get back to work on this set. If you enjoyed this video, please hit the like button. If you'd like to be notified when new videos appear in Mr. Brown's Basement, please hit subscribe. Incidentally, liking and subscribing and commenting really does help out the channel. As always, thanks for watching.